Hi, my name is Aurelijus Stanislovaitis. I do vulnerability testing for Visma, and after my day job, I'm also a chapter leader of the local Lithuania OWASP chapter. And today I'm going to talk about automated and manual security testing of applications. In this presentation, I will talk about one aspect of applications, about security. And from the whole software development lifecycle, I will be focusing only on assurance part, so only on the testing. Security is, of course, wider than this, but this presentation is about testing of security. The purpose of this presentation is to compare strengths and weaknesses of manual and automated security testing, maybe give you some insights, and maybe help you in your decisions about security testing strategy. The contents of this presentation are based mainly on personal experiences. Me, myself, I'm a manual tester, manual security tester. So at the same time, this means that I might be slightly biased to the side of the manual testing. But we'll see how it goes. When I will be talking in this presentation, I will be mentioning quite often two kinds of automation tools. I split them into two broad categories, SAST and DAST. SAST stands for Static Automated Security Testing. This means that SAST tools are analyzing source code and variables. You don't need application to be up and running. You need a source code for SAST tool. Another category is DAST tools. These are dynamic application security testing. Instead, the code, now URLs and parameters are analyzed. So you need the application to be up and running on the infrastructure already in order to be testable with DAST tools. Why this topic? When I joined Visma 2013, huge transformation was already happening. Transformation from on-premise software to software as a service. What's the difference between two? On-premise is a concept from 20th century. It means that software developer, software vendor would write software code, sell it to the customer, and then the customer would install it on infrastructure, run it, manage, administer, and so on. So software vendor does not much more than writing the program and putting it into floppy and shipping it to the vendor, to the customer. Now with the software as a service world, it is radically different. Because in a software as a service world, all responsibility of application code, infrastructure, maintenance, operations, all this lies on service provider's side. And the user now, or customer, has to do no more than open up the browser, connect to the URL, and use the application. So, transition of responsibility for security is very obvious here. In on-premise world, quite a lot of that responsibility would be on customer side. Now in a software as a service world, service provider is responsible virtually for everything. customer is not responsible for security anymore, unless the customer would be so careless to post passwords on the Twitter and so on. So that's not all. Transition from on-premise to software as a service also means that release cycle is becoming faster. Normally, we would be talking about some cloud application. With cloud applications, you're not releasing once per half a year and once per year, as it used to be like 20 years ago. This dictates the same requirement of the speed for testing methods and tools. Therefore, test automation, talk about test automation and implement test automation nearly about, definitely more than 5 years ago. But with the security testing traditionally was always late, always slow. Security testing was always at the end of the all testing cycle, just before the release. So this means that now you have to do security testing more frequently. More frequently and more quickly. Is this achievable? Obviously not with manual testing. You need automation. If you can automate security testing, do it. If you can get rid of people there, that's a good idea. We'll see how it works. And the last one is that security challenges shift to application level. If you're talking about cloud, it's relatively easier to get the infrastructure right. Because you can spawn virtual machines, you make a good config, you spawn virtual machines as much as you can, as much as you need. And they are just copies of copies. But application code is custom. Application code is unique. So if you do infrastructure right, you still have application. Challenge shifts to application level. Now, very briefly, very quickly, kind of obvious, 3 slides of kind of obvious information. When talking about automated and manual testing and comparing scope coverage of those two, humans, they are unreliable. Scope creep is very likely, but they can also traverse through integrations. And one additional drawback is that a lot of still depends on individualities. One tester doesn't equal another tester. Skill set level differs, approaches differ. So you cannot always compare output from 2 different testers. Unfortunately, this probably is not and should not be achievable. If we look into machines, so the scope coverage, narrow but reliable. Usually it's more difficult with testing integrations. And additional challenge is that not all tools support all technologies. If we talk about static source code analysis, you may have some exotic programming language or old programming language which is not supported by our tools. For example, Visual Basic could be problematic with some static analysis tools. Speed. Well, this is really kind of obvious. Humans slow, machines fast. But humans can start right away, with machines, you probably need some time for onboarding. With DAST, with dynamic application security scanning tools, it may take like hours to configure one. With SAST, it may take like days. But once it's configured, once it's onboarded, then it's fast. What about reporting? The unique strength of humans in reporting is that you can avoid false positives. And it's usually that human testers, they don't report false positives. They also tend to group systematic findings together. So let's say you have 50 vectors for cross-site scripting. Machine would, in a machine report, you would have like 50 different issues. As a human tester, could be that you will see this is a systematic issue and report it as one. Maybe give a list of 50 attack vectors as an attachment to that single issue. So numbers are difficult to compare between these two. And of course, humans may have more insight about application logic. Not only about application logic, but they can also understand business logic sometimes, business impact. With machines, with automated tools, it's also, if you use several automated tools, especially if you use SAST and DAST, it might be difficult for you to deduplicate and to correlate those findings. Because SAST tools, they look into source code, and DAST tools, they look into URLs. Sometimes this, quite often, probably most often, this is not trivial. Okay, but having said that, we can already see that some tasks definitely should not be done by humans. Machines are very good into enumerating known badness. For example, enumeration of missing patches on your infrastructure. There are brilliant tools doing that really, really well. And if you try to do that by hand on your huge infrastructures, so then this definitely will fail. Another one similar could be outdated dependencies. Nowadays, applications would have hundreds of dependencies, and to track them by hand to see which versions are outdated and which of them have known vulnerabilities, that's not a bad idea. Leave that to machines. Sometimes this could be not so easy as it may seem, but definitely if you try to do that only by hand, so you again will always be too late and too slow. Remember Equifax, if they have done their patching well, they wouldn't have what they have now. And also, quite mature tools exist to scan infrastructure for known configuration errors. This also can be automated quite easily. So this land is lost to machines forever. Like Garry Kasparov has lost to Deep Blue in 1997, 20 years ago. But like I said, they are more on the infrastructure level. Missing patches and non-configuration issues definitely come to infrastructure level. But when we move more to application level, so then we see that there's no so much of known badness in application level. In application level, there's more unknown badness. These vulnerabilities are not known. They are all unique. They are 0 days. And here in our team, we do testing, and believe it or not, 0 day every day in our team. Every day we find new bugs previously unknown. On application level, of course. But why? application code is custom, so the bugs are. And comparing with operating systems, for example, or such complex programs as, let's say, internet browsers, right? Applications, usually they would receive significantly less attention from researchers, from testers. Less people analyze that. Less people work on these analyses. Less people are looking for bugs there, because applications are custom. If you have operating system, you have billions of installations. A lot of people looking at that, trying to find bugs. And they have gone through long cycles of never-ending lessons, and the code is really mature. Now with applications, these are unexplored territories. And the last one, why it's 0 day every day, because applications are actually buggy. We'll see a bit of more numbers later, but on average, per application, statistics shows that on average per application, you can find 40 cross-site scripting issues, on average. So this means that something is wrong in the kingdom of applications. So I've mentioned exploration, and exploration is the key here. You probably have seen that many times now. Green is something what customer wanted, and green is intended functionality. Now, orange is the actual implementation. That's what developer implemented. And this part which overlaps, so this is good part. Not interesting for me. There's nothing to look for. The green part, I'm not interested in that as well, because functionality was requested, was not implemented. Other QA activities will pick that up. If not, so then customer will complain that features are missing. It's not so interesting for me. And after all, remember, security requirements are non-functional requirements, right? That's not functionality. These are not features, correct? Am I correct or wrong? Yeah. Are they functional or non-functional? Non-functional. Non-functional, but of course, by the book. But then, if we look from attacker's perspective, so security defects is really tangible functionality for attacker. Consider we have payroll application in which, as a regular user, I can log in and check my salary figure. What if it is possible to change from GET request to POST request and set the salary figure? Well, this would be simple implementation error, maybe. I do not dare to say that design could be so much flawed, but maybe simple implementation error. Security defect, non-functional defect. Is that correct? But for attacker, this is very tangible and very real functionality. So we classify vulnerabilities as non-functional, but for attacker, they are really, they can become real features. And that's why this orange part, which is functionality, which was never intended and never specified, is the most important for myself. This does not necessarily need to be a feature as such. It still can be security defect, like lack of output encoding. And because of that, as an attacker, I can execute arbitrary JavaScript on affected victim's browser. Well, for attacker, this is functionality. I wanted to show a bit of numbers. And who is familiar with OWASP Top 10? Quite a lot of people. I would expect that from web developers. By the way, how many web developers? QAs? Others? Quite a mixed crowd. Very good. So OWASP Top 10. OWASP Top 10 2017 is about to be released, because release candidate 2 was released like a couple of months ago, and 3 days ago they released golden something version. But the final version will be released November 20th. So this is a rating of web risks, web application risks. And to compile that rating, OWASP Top 10 project, they had an open call for data sets. Companies across the board could contribute to that. Most of these contributors were testing tool providers or companies doing penetration testings. So there were 24 different contributors who contributed to this call of data. Most of them were either SAST, DAST, or manual testing providers. In total, data set included 2.3 million vulnerabilities. 55,000 of applications were represented in that data set, these data sets. So average is 42 vulnerabilities per application, and 40 of them are cross-site scripting. And I will be using a couple of slides from Brian Glass analysis. He had a brilliant thought to my eye. He looked into those data sets and realized that parts of them is human augmented tools. So this means that automation is primarily mean of finding vulnerabilities. And humans only review for false positives, eliminate false positives, or fine-tune the machine. But the automation is primary mean of finding vulnerabilities. Yet another class of those providers were tool-augmented humans. This means that vulnerabilities were actually detected by humans, but humans were using tools, sophisticated tools to make it faster and stronger. And there's a huge asymmetry here, because 91% is human-augmented tools. This means automation. Almost all of that comes from Veracode, to be frank. So he counted those vulnerabilities and came up with this table. So you can see now that here we have a list of vulnerability classes or vulnerability types. And these two columns, orange human and gray machine. Now, if the number is green on human column, this means that humans are more effective finding these types of vulnerabilities, because, for example, with Crosssite forgery vulnerabilities, humans were able to detect 70% of all Crosssite forgery vulnerabilities in those data sets. Machines were able to detect only 29%. So comparing those two columns, you can see that machines beat humans almost in all categories, with the exception of probably insecure, missing function level access control, improper function level access control. But this sort of no surprises, because you need to understand application context, and machines are not so good in that. What's slightly more surprising is that Crosssite forgery, because Crosssite forgery is a technical problem. Machines should easily detect that, in my opinion. But yes, but of course you need to have some insight about whether this request is, whether it changes data or not. Well, static analysis tools do that, but you need to fine-tune them. And what is really surprising is that under DOM cross-site scripting, again, cross-site scripting, it appears that humans are still better into finding DOM cross-site scriptings than machines. For some reason, JavaScript analysis, static JavaScript analysis is still challenging for automation. Does anybody in the room know good JavaScript security static analysis tool? I haven't seen such yet. I remember talking to Veracode in 2015, and I said, well, you are good, guys. You are really good. But what about JavaScript analysis? Do you have anything for JavaScript? They said, oh, yeah, we're working on this. Really, in 1.5 years, we will have it. Then in 2016, in AppSec in Rome, I go to their booth again and say, you're probably now pretty close to JavaScript Analyzer. I said, yeah, we're working on this. In 1.5 years, we will have it. Stop talking to them after that. Maybe they have it now. But so these numbers, machines are winning. But then Brian Glass had sort of revelation that, remember, automation tested 90% of applications, and humans tested only 10% of applications. You cannot compare those figures, because if humans have been tested as many applications as machines, so then maybe results would be 10 times bigger on human column. And he did that. He just multiplied by 10 times human column. And now we have different table. Here you still see machines on a gray column and humans on an orange. And now almost all orange column is green. So what does it actually mean? This actually means that if only we could have enough of human testers, probably we could still have very, very good results, even better than we get from automation. This is, of course, utopia. And sadly but true, humans don't scale. So it's not possible to have a huge army of humans doing the same job as automation can do. But then, so how do we work with this? Maybe let's be pragmatic and practical. If machines can find or can cover 90% of the work, maybe that's sufficient. See? Let's cover 90%. Maybe 10% is not so bad after all. 10% uncovered. Could be right, could be wrong. Here's that defender's dilemma. An attacker needs only to find single weak point, attack it, and break it. But the defender needs to know all weak points and defend all of them. This is why guerrilla warfare is effective. You have a small group of fighters against a huge regular army. You avoid massive confrontation. Instead, you find a weak point, quickly attack, and retreat. That's why attackers can win. But that's not all. There could be something more. There's also Nakatomi Space. Who's familiar with Nakatomi Space? Die Hard. That's correct. That's correct. So Bruce Willis is playing John McClane, right? And these bad guys, they have taken the huge building called Nakatomi Plaza, and they are holding hostages there. McClane can help them all, but unfortunately, attackers control all corridors and elevators, and he cannot use normal ways to move across that building. So what he has to do, he moves not in the normal corridors, but he moves in those technical spaces, in those areas which architects were never designing for people to walk in, to crawl in, or to jump into. And he's exploring that Nakatomi space, that alternative space where you can traverse the building in a previously unknown ways. If there's no door, he makes it by blowing half of the wall. And our applications actually have plenty of that Nakatomi space, if you would look from that point of view. Consider about undocumented APIs. Consider about go beyond limitations of UI. Tamper with the parameters. You will find that Nakatomi space. You will see that you can traverse through your application. But more important from this is that if you have one guy which is really desperate, and, well, if we are talking about attackers, about criminals, they often can be desperate. Nobody does that for fun, I guess. So if you have a desperate guy, he will find a way through. I've learned that from the positive perspective, that if you have a desperate tester in your team, he will find bugs eventually. Think about Nakatomi space. Oops. Okay. But then, so this means that we need to protect against human attackers. So we need to test with those human methods as well. But overlap is expected, I would say, because machines are good in testing cross-site scripting. But I'm also very good in testing cross-site scriptings. So machines can do that faster and cheaper. Let the machines do the job. Okay, let the machines do the job. I'm not testing cross-site scripting anymore because overlap exists and I'm only doing the part which doesn't overlap with machinery. But in reality, we tried to compare results from static analysis, from dynamic analysis, and from our manual tests on the same applications. And here's an illustration. The tester was testing an application, and he found two cross-site scriptings. One was in sort of a JavaScript redirect. You can see here request and response. So in the parameters, after settings, you can write JavaScript commands, and then without encoding and escaping of characters, this is put directly into JavaScript to do redirect, because this is triggered only when user is logged off. So redirect is happening to login page. So that's kind of JavaScript redirect vulnerable to cross-site scripting. And you get a pop-up, of course. You can execute JavaScript. Another one from that application was that user input had to originate from integrating application, from another application. And then under some error condition, you again would find a place where input is not, or output is not output encoded. Cross-site scripting again. So two cross-site scriptings were found in that application. Now after that, or to be more precise, during the same time, the application team onboarded to static analysis tool as well. So when the manual tester had his results, static analysis tool also had results already ready. And there were two cross-site scriptings as well. So we looked into the results from static analysis tool, and we found two almost identical code fragments with this item value not being encoded and hence cross-site scripting. I will sit for like 5 minutes staring, but this doesn't make sense. This doesn't map anyhow. That's a different place in application. We didn't find that. Static analysis found. But these are different things. So this means that 2 doesn't equal 2. And what more it means that the overlap, realistic overlap probably is not like this, but it's more like that. Overlap is either small or no overlap at all. So probably you cannot avoid having automation, SAST, DAST, or humans. I'd say you need to have all of them. And you will still have plenty of space in your bug universe, which is left uncovered after all of your efforts. So what can we do more? Who remembers, given enough eyeballs, all bugs are shallow, isn't it? Maybe we can crowdsource security testing. Wouldn't that be a great idea? We already see some numbers supporting that humans can actually be really good in testing. The main problem is that you cannot scale them. You cannot have an army of them. But with crowdsourcing, maybe that would be possible. Maybe you can do that. But do you want to do that with security testing? Because that's security testing, that hush, hush. You cannot crowdsource security testing, right? Or can you? You can, of course you can. Why not? Many companies do that. And there are bug bounty platforms, HackerOne, CNAC, Cobalt, BugCrowd, and so different platform providers where you as a company can register and give your products for testers to test it, and then when they report bugs, you validate that the bugs are correct, that the bugs are true, and you give them bounty awards. You pay them money. And testers can be anyone who's registered to that bug bounty platform. And bounties, size of bounties are awesome. Look, Google increases maximum Android bug bounties to 200,000 because Microsoft did that with a couple of their bug bounty programs. And you can find bugs for Pentagon as well. They're not so rich, so they're offering only to 15,000. But the main message is that you can crowdsource, because many companies are doing that already. And to support this even more, the black market of web application bugs exists. We've seen black market of operating system bugs and all of that non-web things. And web application vulnerabilities were sort of not so much visible in that sense. But the black market really exists. And you can see that Ethereum cryptocurrency suffered real damage because of Crosssite scripting. Attacker was exploiting Crosssite scripting. You can buy hacker as a service. You can buy criminal hacker as a service. I doubt that this is very legal service, to be honest. And you can see that there are a lot of people building up their reputations, like this Yumba guy, Russian-speaking hacker, developing tools for web injects, and prices upwards $1,000, right? So the black market exists. These are just examples. So if the black market of web application bugs exists, so maybe it makes sense to buy our bugs back before criminals do that. Well, for me, it starts making some sense. I was skeptical about bug bounty programs for a long time, but now I'm not. Okay, so humans and machines. They have unique strengths and unique weaknesses. Humans report no false positives. Humans are context aware, and humans can crawl through Nakatomi space effectively. Machines are fast, scalable, and good for repetitive tasks. Use a combination of both. And the complete picture, of course, it's not only testing. Security is only little part of security is testing. It all starts, of course, from training and awareness, so that you train your developers, you train your product owners and business analysts. From there, you can build good security requirements and coding conventions, so that your code would contain less security defects. And from there, you can do code reviews after you have the competency. Once you've done with this, you can start with assurance part and start from SAST, DAST, manual testing. SAST, you can use this earliest because once you have source code written, you already may use SAST, static source code analysis. Dynamic application. Once you have your code running on infrastructure, you can start using DAST. And leave manual testing maybe for later, because they anyway are still slow and late, so do automation first. But verify with manual testing. Bug bounty. The general advice is not to do bug bounty if you don't have these in place, because otherwise it may appear that your application is so buggy that you will give away to bounty hunters $100,000 in 1 month and run out of your budget for the whole year. So that's more complete picture I would like to see. And that's what we are also trying to build and what we are doing in our company as well. And that's the end of my presentation. I would be happy to get any questions if we still have some time. No questions. How many of you use security testing automation in your products? Maybe some names of tools? 45. Okay. Sonar. So you're more on that static analysis, not dynamic.
Oh. We have testers too.
Okay.
Can you recommend some tools?
Well, from static analysis, I'd say that Fortify is. I'd say that Coverity, for example, I think was the only one service provider mentioned in one of this NIST reports about contemporary web application security techniques. But then Veracode as well. Veracode for binary analysis. So I'd say that there are options with the static. With dynamic scanning probably is less mature technology, and you would get more of superficial findings from dynamic scans, unless they are really heavy augmented by humans. As, for example, White Hat Security have a platform which is automation, but then they put some human testing on top of that. But they are significantly more expensive than pure automation providers, let's say Tinfoil or Detectify.
When it comes to acceptance tests, you have this this chart where automation test automation helps in 90% of the to find the bad cases. But this is for security testing, I guess. And when it comes to acceptance tests,
You mean this?
yeah,
Are you talking about this?
I was talking about the table and
This?
yeah, only 10%.
Yes, this is
By human.
this is only security testing, and this is the numbers are from those data sets which providers contributed to OWASP Top 10,
Yeah.
and from those data sets, it was that 90% of all applications was covered by those human augmented tools, so to say. The better code was actually the vast majority of all results.
But do you have numbers for not only for security testing but for
No.
acceptance tests?
No. And these numbers actually, they also could be arguable if this extends to, if these are representative enough, because these were only from those contributors who contributed to OWASP Top 10. But of course, 55,000 applications, 2.3 million bugs. So this is an impressive data set anyway. But no, I don't have, because like I said, I might be slightly biased because I do testing myself, manual testing of security.
Yeah.
Yes?
This black market of bugs, can I just Google for it and I find it?
Yeah, you go to that dark web and with your Tor browser and you can find them. I do not recommend using them, so I cannot recommend.
But it seems to be cheaper than hiring crowdsourced, right?
Yeah,
If you do find the market.
for hire thieves to do work for you.
I guess it's risky that
You could end up with the money in their pocket.
If I may, we're using HackerOne, so crowdsourcing at Trustpilot. I work at Trustpilot, and we're using it for a year or two. I'm not that long with the company, but I was told that the highest amount we paid for as a bug bounty was $500.
500.
So
Yep.
I guess it's up to the company to decide.
It's up to the company, and it's also up to the bug type of bug. If you report simple cross-site scripting, so then maybe you can get like $50 or 100 or 150. If you do remote code execution, then maybe 5,000. But again, it differs from provider to provider. Franz Rosen, for example, I had a chance to talk to Franz Rosen a couple of months ago in Berlin. He said his highest was maybe 30,000. But that was like a complete takeover of everything. I think we're out of time now, and thank you for attending this presentation.